Hello, my name is Chris Fattinger. For our project, I worked with Kimmy Fawn and William Poveda on investigating the effects of incorporating a two-mass damper on the top of a building to reduce the response due to seismic excitation. When a structure is subjected to an earthquake or to the action of strong winds, a certain amount of energy is introduced into the structure. For moderate to strong earthquake or wind excitations, a substantial amount of the total energy introduced in the structure is dissipated as hysteric energy. Physically, it represents energy dissipated through nonlinear behavior of the structural members after yielding, and the more hysteric energy dissipated, the higher the structural damage. The displacements and the accelerations can become very large, especially if the dynamic load frequency matches the structure's natural frequency, which results in resonance. Passive energy dissipative devices try to concentrate the dissipation of hysteric energy in a few chosen and well-designed elements. The remaining portion of energy can be absorbed by the structure in elastic or near-elastic behavior. The tuned mass damper, or TMD, is such an energy absorber, consisting of a mass, a spring, and a viscous damper. The TMD is a large, massive block which is usually mounted on the top or near the top of a tall building. Its frequency can be tuned to match the predominant vibration frequency, which is usually the first modal frequency of the main structure, so that the structural dynamic responses caused by environmental excitations such as strong winds and earthquakes are significantly reduced. The TMD was first suggested by the German inventor Hermann Frahm in 1909 to attenuate undesirable vibrations in ships. The device consists of a mass, springs, and damping devices. While attached to the main system, the dynamic behavior of that system can be altered. Up to now, TMDs have been successfully installed in many civil engineering structures to control the structural vibrations due to environmental disturbances. This is especially true in many tall structures worldwide, namely the CN Tower in Canada, which is 535 meters tall, the John Hancock Building in Boston, USA, which is 60 stories tall, and the once tallest building in the world, the Taipei 101 Tower, which is 101 stories or 508 meters tall. In this presentation, we will analyze the effectiveness of using a TMD to reduce the displacement of building structures under seismic excitation. To analyze our system response, we will focus on the San Andreas fault line, which is the most active earthquake zone where the biggest earthquakes in California have occurred. We will use the acceleration data from the earthquake in El Centro, California in 1940. This earthquake was a magnitude of 7.1 and caused tremendous damage. 80% of the buildings were damaged to some degree. We will support our findings with a published article about this subject by Christian Pastia and Septimiu George Luca from the University of Lazio, Romania. We will then use these results to predict the displacement of the one Recon Tower in California would be if the same earthquake were to happen again. Our research's subject of study is the One Recon Hill South Tower. Its completion date is 2008 and was the first building in California to have a liquid two-mass damper. The TMD system of the One Recon Hill Tower consists of two 54,000-gallon tuned liquid damper tanks. The TMD used baffles inside the liquid tank to control the sloshing effect to oppose the building motion. Baffles are commonly used as a device to control the flow of fluid in a particular direction. This is an important feature to consider during the design and construction process, because the One Recon Tower, as mentioned, is located on the San Andreas fault line. To model our system, we consider the motion of the structure only in one dimension. This means, for example, that we did not consider the motion of the building in the vertical direction, and we assumed that the torsional effects on the building were negligible. We used a state-space model approach to model the system. Our input vector is the ground acceleration from the seismic excitation. We only looked into the system response of the peak maximum acceleration of the El Centro earthquake. The peak maximum acceleration is equal to the maximum ground acceleration that occurred during the earthquake shaking at that specific location. In this case, the maximum ground acceleration during the El Centro earthquake was 0.3495 meters per second squared. We analyzed the response of our system based on the worst case scenario that this maximum ground acceleration occurs instantly as soon as the earthquake waves reach the structure's location. After going through the free body diagrams of our system, we obtained the two equations of motion as seen in equation 1. We then continued to develop the state-space model of the system. The A, B, C, and D matrices of the state-space model can be seen in equation 2. Before we move on to explain how we determine the values to solve the state-space model, here are some variables and definitions of our system for the hand calculations. M represents the mass of the building. K represents the spring constant of the building. C represents the damping constant of the building. MD represents the mass of the tuned mass damper. KD represents the spring constant of the tuned mass damper. CD represents the damping constant of the tuned mass damper. XG represents the ground displacement. X represents the building's displacement. XD represents the tune mass damper's displacement. To solve for K, KD, C, and CD, we decoupled the system and treated the building as one system and the tune mass damper as another system. Then we solved for the values as simple spring mass damper system for a second order system in standard form. We also introduced a few new variables. These are F, which represents the building's natural frequency, Rho, which represents the ratio between the building's frequency and the frequency of the tune mass damper, Mu, which represents the mass ratio between the building and the tune mass damper, Zeta, which represents the damping ratio of the building, and Zeta D, which represents the damping ratio of the tune mass damper. To determine the values of the parameters in our system, we referenced to Table 2, which shows the optimum TMD tuning and damping ratios. We decided to choose a mass ratio of 0.1 and a value of 0.05 for the damping ratio of the building structure. From our research, we found that the one recon tower has 2 tanks of liquid damper. Each contains 54,000 gallons of liquid water. From here, we converted gallons of water to mass in kilograms, and obtained a mass of 4.088 times 10 to the 5th kilograms for the damper. Then applying the mass ratio formula for our chosen 0.1 mass ratio, we can estimate that the mass of the one recon tower is 4.088 times 10 to the 6th kilograms. We took this extra step since we were unable to find the mass of the one recon tower during our research. As seen in Table 2, for a mass ratio of 0.1, the value for the ratio of the tune frequency Rho is 0.8954, and the damping ratio of the tune mass damper is 0.3466. Since we know that the ratio of the tune frequency Rho is the ratio of the frequency of the tune mass damper to that of the building structure, we can then solve for the fundamental frequency of the building. To accomplish this, we referenced a manual on seismic building design that referenced building codes such as the American Society of Civil Engineers, or ASCE. These are building codes that engineers must follow when building a structure to ensure safety. The ASCE manual recommends to use Formula 7.2.37 to estimate the fundamental natural period with what type of building materials and how many stories the structure has. We know that the one recon tower has a total of 61 stories and is a concrete type structure. So we calculated the natural frequency to be 1.7167 radians per second, or 0.2732 Hz. Now we can calculate the required frequency of the tune mass damper by applying the tune frequency formula. From this, we find that the necessary TMD frequency is 0.2446 Hz. We now have the necessary values to calculate the values for the stiffness of the building, the required damping coefficient of the building, the TMD damping coefficient, and the TMD stiffness. Using the decoupled equations 3 through 6, we find that the necessary values of the parameters are as seen in tables 2A and 2B. This is a continuation of the previously calculated parameters. We solve for our system numerically using the ODE45 solver in MATLAB. We solve for the displacement of the building using a maximum ground acceleration of 0.3495 meters per second squared from the EI Centro earthquake. As seen in Figure 9, we have included our A, B, C, and D matrices of our state space model. In order to determine the effectiveness of the tune mass damper, we solve for the displacement of the building with and without the tune mass damper. As seen in Figure 10, the displacement of the building is significantly reduced due to the addition of the tune mass damper. To clearly show the effectiveness of the tune mass damper, we calculated the percent reduction of each peak and trough from the plot our MATLAB program produced. We focused mainly on the first 10 seconds, since this is where the maximum displacement occurs. As seen in Table 3, there is a displacement reduction of 11.5% during the first peak. Then for the second and third peaks, the displacement reductions increased to 43.4% and 61.1% respectively. As time continues, the displacement reductions continue to increase. These values are ideal, but we have to keep in mind that this is a simplified model of the tune mass damper system. In this presentation, we have only considered the motion of the building in one direction. As seen from this experiment, a proper tuning of a tune mass damper can provide significant reductions in the displacements due to the seismic excitation occurrences in buildings. Due to this, tune mass damping systems have been incorporated into many tall buildings. Given our analysis in choosing the optimum parameters for the One Recon Hill Tower in San Francisco, California, we can see that if the same EI central earthquake were to happen again, the One Recon Hill Tower would experience a significant reduction in the displacement thanks to the addition of the two 54,000 gallons of tuned liquid damper tanks at the top of the building. This is a list of the resources used for the research conducted in order to complete our analysis. Thank you for your time and attention during this presentation. Have a good day.